Okay. Hi, everyone. Thanks for being here. My name is Tim Becker. I'm a security researcher at ChainLight, and today I'm going to talk about ZK security. So I'm going to start with a very quick overview of zero-knowledge proofs, just to get everyone on the same page. So there's two parties, a prover and a verifier. And X denotes some public data that the verifier is going to see that some property about is being proven. W is witness data. So this is some supplemental data used by the prover to verify that property about X, but is not necessarily disclosed to the verifier. And the way that it works is the prover takes the public input and the witness data and generates a proof pi that the verifier can then verify against the public input and either reject or accept the proof. And all proof systems, pretty much in all of computer science, need to have two properties, completeness and soundness. So completeness says that all true statements that you care to prove can be proven, and soundness says that only true statements that you care to prove can be proven. And the magical properties of zero-knowledge proofs that lead to all of the amazing applications are succinctness and soundness. So in short, succinctness says that the proof is very small and very cheap for the verifier to verify. So they need to do a lot less work than the prover. And the zero-knowledge property, of course, is where it derives the name, and it says that the proof doesn't reveal any unnecessary information about the witness. So the witness is this data that the verifier doesn't see, and ideally they should not be able to recover any information about it other than exactly what is necessary for the proof. So how do some examples fit into this? In a layer 2 blockchain, the prover is usually the sequencer or some party associated with the sequencer, and the verifier is an L1 contract. And essentially, they're proving the block transition function. So the public data are essentially two consecutive block roots, and the witness data is some validation trace, like the trace of a program that validates the block transition function. And soundness here guarantees that only valid blocks can be finalized on the L1. So the L1 isn't going to have some incorrect view of the state of the L2. And completeness says that all valid blocks, so anything that can happen on the L2 can actually be proven by the prover and finalized on L1. Another example, this is like privacy-preserving identity. So say your application wants to verify a user is at least 21 years old, and the public input here is some like pseudonymous user identity, like a username or something, and the witness data is some signed data that attests to their age. So for example, a passport contains an NFC chip that transmits a signed payload attesting to a bunch of facts about your identity, and you can verify that in a zero-knowledge proof and withhold all of the sensitive information about you except for the fact that you're over 21. So here, soundness guarantees that only users that actually have this signed attestation can authenticate to your application, and zero-knowledge protects the user from revealing information about themselves that they don't want to reveal. So what can go wrong with zero-knowledge proofs? I have three threat models to talk about. One is input, basically leaking of this private input data. So in the previous application, this would mean that an attacker can recover more information about the user than just their age using this proof data. And here the attacker can either be the verifier themselves or some other third party that can see the same data as the verifier. Another threat model is malicious input. So in this model, the prover is not in full control of this public data that they're proving information about. So like a sequencer isn't in full control of the transaction data because users can submit transactions to the layer 2 that the prover is going to have to be able to prove. So if an attacker can produce some transaction that they know the proof system won't be able to handle, then they can break completeness because the prover won't be able to prove that, and this can cause like a denial of service on a layer 2, as an example. And the third threat model is a malicious prover. So in this case, it's either the prover themselves, like in an authentication application, anyone can be a prover. If it's like a sequencer, even if it's a permissioned prover, this model can assume that that prover was compromised somehow. Like maybe their signing key that they used to relay the proofs was extracted, and the attacker can now create proofs and relay them to the layer 1. So in this model, the attacker is trying to break soundness and convince the verifier of some fact that is not true. Yeah, so to see how these things can actually go wrong, we need to look inside a ZK proof system. And I think it's conceptually helpful to divide it into two pieces, the front end and the back end. So the front end is essentially the part that the developer of the ZK application interacts with. So this can be circuit libraries where they write ZK circuits, or it can be, these days, higher level ZK VMs. So these are essentially like interfaces that will allow you to write regular like Rust code and compile them to a virtual machine that then gets proven using some underlying zero-knowledge circuits. And the back end is essentially what takes these constraints that get outputted from the front end and does the cryptographic magic necessary to actually prove it. So there's a bunch of proof systems. I'm sure you've all heard of Plonk, but there's a ton of variants. There's new proof systems coming out all the time, and these are essentially what the back end implements. And yeah, bugs can happen at any layer of the stack. So they can be in your application, the front end, or the back end. So front-end bugs are often overlooked, but they can be quite critical. And these can happen where even if you wrote your application code correctly, the front end compiled them into constraints incorrectly. Or in the case of like a ZK VM, it can mean that the circuits that verify the integrity of the VM computation have a bug. And I also include standard library vulnerabilities in the front-end bugs because even though standard libraries are kind of like application code that use the front end, they are usually packaged with it and part of the same trust assumptions that you're making as a developer when you choose a front end. And there's a famous example of a front end or a standard library vulnerability in circomlib where their MIMC hash function had a soundness bug where a variable was assigned but not constrained. And this actually made Tornado Cache vulnerable to double spend attacks. And this vulnerability was actually self-exploited by the Tornado Cache team to safeguard the funds and upgrade the protocol. There can also be bugs in the back end. So the back end is generally just implementing a proof system. And one crucial detail that can go wrong in these proof systems is something called the Fiat-Shamir heuristic. So proof systems, whenever they're like studied academically and peer-reviewed, are usually studied as interactive protocols. But in practice, zero-knowledge proofs are used as non-interactive protocols, which essentially means the prover produces a single proof with no interaction with the verifier and just sends them a single payload that they can verify. And the thing that makes this possible is the Fiat-Shamir heuristic. And this is like a sort of very deep topic in cryptography. And it is often left as an implementation detail when these systems are studied academically. And it famously can go wrong in a ton of ways. And actually, just recently, there was a paper proving that even very natural, like seemingly correct uses of Fiat-Shamir can be vulnerable. And even more recently, this week, I saw there was a paper talking about how to defend against attacks like this, sort of very generally. So this space is kind of developing very rapidly. It's just something to be aware of and keep an eye on. And of course, the most common place for there to be bugs in a ZK application is in the application code itself. So usually this is where you implement your logic that you're trying to constrain or prove incorrectly. Generally, this means you're under-constraining something. Like it's more common for you to under-constrain something. An example is like missing a range check on some value. So a range check ensures that a certain variable isn't too large or isn't too small. And this is a very common type of constraint that people miss. Sometimes you can over-constrain variables. An example would be like if there's some edge case in what you're trying to prove and you forget to implement that in your circuits, then you're unable to prove any data where that edge case occurs. And another category are integration issues. So this is where even if the zero-knowledge proof itself is correct, it requires you to write your application in a certain way. So an example is in systems like Tornado Cache, there's a value called the nullifier, which essentially proves that you have made a deposit. And the proof system itself doesn't check that you only prove that once. It doesn't check that you only use this nullifier once. And so that's up to your application code to sort of the thing wrapping the zero-knowledge proof system to check that this value is only used once. And there are many ways for that to go wrong as well. So I want to give a quick example of what a soundness bug can look like and how it can be exploited. So this is a bug that ChainLight found in zk-sync era, an early version of zk-sync era. And basically, it's an application layer bug, but I view it as sort of more of the fault of a footgun in the front-end standard library. So there's something called a linear combination gadget. And it was very easy to forget a call to a certain function that actually generates the constraints. Like you could construct the linear combination, but forget to constrain it. And this linear combination was used sort of to decompose a 256-bit value into two 128-bit values. And this code here creates a linear combination that's supposed to check that that decomposition is happening correctly. But they forgot to call the enforce 0, so no constraints were actually generated, which meant that the highest 128 bits that get written into memory in the zero knowledge VM were unconstrained, and the prover could put whatever they want there. So this is a very small bug. It's like one small constraint that's missing, but it actually has critical impact. So basically every smart contract on a layer 2 uses memory writes. And on zk-sync era, there's something called system contracts, which are privileged contracts that perform very sensitive operations necessary to the L2. An example would be withdrawing ETH from the layer 2 to the layer 1. There's this system contract, and basically it burns your ETH on the L2 and generates this withdraw message that gets put in the block root that then you can finalize on layer 1. And this withdraw message gets written into memory. And so a malicious prover would be able to manipulate the amount of ETH that gets written in this withdraw message, and then on layer 1, prove that invalid block and finalize the withdrawal that withdraws more ETH than they were attempting to withdraw. So it's just a one-line fix. It's just to call this function that actually generates the constraints. And we reported this vulnerability to zk-sync era's bug bounty program very early on. They were one of the only chains that had a bug bounty program, and especially 4 zero-knowledge circuits, so big kudos to them for that. And we actually fully implemented the exploit for this as kind of like a public service, like to demonstrate how zero-knowledge exploits can look and like hopefully educate people on the risks. So zk-sync era at the time actually had a very crucial mitigation, and this is another big testament to their their efforts in security. So they had something called an execution delay, which means that there's a time lock after the block is proven before anything in it is considered finalized. And what this means is that if they have good monitoring that can check if an anomalous block was proven, they can intervene before any of those withdrawals or any other transactions are finalized. So one concern around this is that you have like the centralized governance or security council that can intervene. And you can actually do something really cool with zero-knowledge proofs called self-cancellation. So this is where if you can prove multiple independent block roots for the next block, that implies that there's a soundness bug. And so during this execution delay, you can not allow any intervention unless you're able to prove 2 different blocks, and only then do you allow intervention. So it's this extra kind of security layer that reduces centralization risk from a security council or governance. Another really important mitigation you can have are called multi-proofs. Multi-proofs are kind of like multi-sigs for wallets, but with proof systems. So the attacker has to compromise all of the proof systems at the same time, meaning they have to prove the same invalid data, say, like, for example, the same invalid block root in all of the proof systems at once, which dramatically reduces the risk of there being a bug. So the ideal is that you have completely independent implementations of the full ZK stack. So you write separate application code and use separate front ends and back ends. This is, of course, like a really big ask because even having the same team implement both is introducing some risk that they implement the same bug in all the systems. So a slightly easier first step that a lot of L2s are currently working on is using TEE attestations as a second factor. So This doesn't require doing a full ZK proof, but it does add some security to your proof system because a TE attestation, in theory, should be difficult to forge, and especially difficult for an attacker to forge that while also breaking a ZK proof system in the exact same way. It's worth noting there is a trade-off you're making here. So if you require multi-proofs, it means you need to be able to prove the block with all of the proof systems at the same time, which means you're risking, if there's a completeness bug in any of the proof systems, then you're unable to prove that block in your multi-prover. But generally, soundness bugs have higher impact and are more critical than completeness bugs. So this is generally a trade-off worth making for security. And there's even sort of self-cancellation type things you can do where you only, basically, like if there's a completeness bug, you can also confirm that because the no proofs have been finalized for a long time, and then you can allow an upgrade that fixes the completeness bug. So I want to end with some general recommendations. So if you're a developer writing a ZK app, you should choose very battle-tested front ends and back ends. This means they should have multiple high-quality audits and ideally be in scope for a very large bug bounty. Another good thing to see is if there's formal verification of some of the components of the front end or back end. It's kind of infeasible still to do end-to-end verification of a ZK application, but you can do smaller things like formally verify that the verification logic, like the smart contract that verifies the proof, is correct. Of course, you should get application layer audits. Zero-knowledge bugs are very subtle, and it's likely that one audit won't catch them all, but audits are still the best way to find zero-knowledge bugs. If you look at any of the audit reports from ourselves or other good ZK audit firms, they basically always find bugs or highlight important failure modes that are crucial to be aware of. Multi-provers, so again, the minimum is a ZK proof plus a TEE. This significantly raises the bar for attackers. The ideal is you have separate teams implement your full ZK stack independently and do multiple zero-knowledge proofs as part of your multi-prover. And yeah, the last line of defense, if possible for your application, is to have some sort of finalization delay and monitoring where you can detect an anomalous proof has been submitted and do some sort of intervention. Yeah, so I can take any questions. You can DM me on Twitter or catch me off stage if you want to ask anything else. Thank you.